Okay, so for chapter 12, it's all about alcohols from carbonyl compounds. This slide is prepared by Sir Valles and the others, but this is again pattern. The reference is still from Solomon's. And by the way, please make sure again that you will study on the reactions of ethers. So it's just similar to the reactions of alcohols using the substitution reaction. Okay, so last chapter, in the previous chapter, we talked about the preparation of alcohols. And usually the one that we have described in the previous chapter, in chapter 11, was about the preparation of alcohols from alkene. No? We have the hydration reactions of alkene, and then hydroboration reaction, oxymercuration, demercuration reaction. So we have that preparation of alcohols, usually from alkenes. And then you can also prepare your alcohols, of course, from your alkyl halides, your RX, using the substitution reactions. Now, other than those reactions, it's also actually possible to prepare our alcohols from carbonyl compounds. And in this kind of reactions, we will be dealing with the oxidation reduction in organometallic compounds. Now, what is this organometallic compounds? Or the oxidation reduction reaction, of course, you're familiar with this one. We're talking about the oxidation. No? When we say oxidation, it's always accompanied with a reduction. It's the loss or gain of electrons by the substances. If one reagent accepts electrons, the other, of course, will lose the electron. And we're usually dealing with carbonyl compound. So there are several functional groups containing the carbonyl compound. So what is the carbonyl compound? Whenever you have the C double bond O, okay, you call this one as a carbonyl group. Okay, so the carbonyl group, you can have your aldehyde. Remember, you have your R, C double bond O, H. The aldehyde is a terminal carbonyl group. Okay, and you have your ketones, C double bond O, and carbon is bonded to two alkyl groups. You can also have your carboxylic acid. Your carboxylic acid, you have your C double bond O, and the other group that's bonded to carbon is the OH, carboxylic acid. Or you can have your carboxylic ester, it's your ester. You have your C double bond O, and bonded to carbon is the OR, the alkoxy group. Okay, so you have your aldehyde, ketone, carboxylic acid, and the esters. So for the structure of the carbonyl group, we have learned in Chem 130 that whenever your carbon is bonded to 3 atoms in a double bond, it assumes a trigonal planar shape. And of course, for this trigonal planar shape, it utilizes sp2 hybrid orbitals. Your carbon is bonded to the oxygen using double bond. So here you have your pi bond actually, and you have your sigma bond. So this two bond is comprised similar with your alkene. No, you have your sigma bond, and you also have your pi bond. So there's two types of bond that's being utilized between carbon and oxygen. And of course, you learned that the pi bond is made by the unhybridized p orbital of this and hybridized p orbital of your oxygen. They do sideways overlap up and below the plane, and that's actually your pi bond. And then the other one is a sigma bond that's comprised of a head-on overlap between the sp2 hybrid orbital of this and the sp2 hybrid orbital of this. It's a head-on overlap. The pi bond again is the sideways overlap, the p orbital and p orbital of this, the unhybridized p orbital. And then you have your sp2, another sp2 sigma bond here bonded to another bond, another carbon here, depending kung sa pwedeng carbon here, whether it utilizes an sp3 or sp2, but this carbon utilizes an sp2 orbital to form a bond with another group here, and another sp2 to form a bond with another group here. So basically, again, because your carbon is bonded to three atoms here, it utilizes trigonal planar, and the bond angle you expect is around 120 degrees. No? So now my variation gamay, but more or less it's close to 120 degrees. So the carbonyl group is actually polarized. Of course, whenever you look at the structure having the oxygen in it, you expect your oxygen to be electronegative. Of course, being an electronegative atom, it possesses a partial negative charge, and of course, the electron density between carbon and oxygen will be drawn toward your oxygen. So oxygen will bear a partial negative charge, again, by virtue of oxygen being an electronegative atom, and the other carbon atom will bear a partial positive charge. So you can actually see this effect, no? That you can have a resonance structure for the carbonyl group wherein your oxygen will bear 6 electrons, unshared electrons in a negative charge, and carbon will bear a positive charge. So this is a resonance structure for your carbonyl group, no? But however, you've learned that the important contributing structure is for a structure wherein the carbon doesn't bear a charge, and all of the atoms doesn't bear a charge between this structure or this structure. The first one is always the most important structure. In fact, this one is almost negligible. But although this is a contributing structure, this is a resonance structure, this one, your carbon, this structure will always be more important than this one. And in fact, for this, you will have a hybrid using this one. So your electron will be shared here. You will have a partial negative and a partial positive charge here. And the evidence for the polarity can be seen with the large dipole moments associated with carbonyl compounds. So for instance, you have your formaldehyde, your ketyl bond OOH, no, it's an aldehyde. You learned about naming in the organic chemistry laboratory. It's an aldehyde. The dipole moment, mu, this is a measure of how polar your compound is. Now the dipole, the net dipole is directed towards your oxygen here. So it's 2.27, it's very large. For acetone, you have ketyl bond O, CH3 here, it's a ketone. And of course, this is not trigonal. Now this is not tetrahedral, and it's planar. The dipole again is towards your oxygen here, and the dipole is very large, 2.88. No? And if you look at on the electron density map of your molecule, let's say acetone, you'll see that more electron density will be directed towards your oxygen. Now you can see the red map here, which indicates that more electron density actually can be seen with your with your oxygen. So the reactions of carbonyl compounds can be associated with nucleophiles. So the carbonyl groups can undergo nucleophilic addition. What is that nucleophilic addition? So nucleophilic, which means that you will be dealing with a nucleophile. What is a nucleophile again? Do not forget what is a nucleophile. The nucleophile is an atom which is electron rich, no? Electron rich, yeah. So it can either be negatively charged. Most of the time it's negatively charged, but it can also be neutral. So a nucleophile is a group of atom or atom bearing electrons with it, no? And it will attack a positive center. Okay, so here, for example, between the carbonyl group, no, it's always a carbon that bears the partial positive charge. So the nucleophile will always seek a positive carbon, partially positive carbon. And when this nucleophile will attack the carbon here, what happens is that the bond between carbon and oxygen, its pi electrons will be converted back into unshared electrons, and would result to having from 2 unshared electrons, so you get 3 unshared electrons on oxygen and a negative charge on the oxygen atom. So the pi electrons, this is what I have been saying, will be shifted to oxygen, okay? And the carbon becomes sp3 hybridized, therefore tetrahedral. So from a trigonal planar, no, that utilizes an sp2 hybrid orbitals, what will happen during this reaction is that it will be converted into a tetrahedral in shape, and of course utilizing the sp3 hybrid orbitals. So hydride ions and carbon ions are actually two examples of nucleophiles that react with carbon. So instead of hydride ions, it's hydrogen with 2 electrons and a negative charge. Carbon and ions is a carbon with 2 electrons and a negative charge. Okay. So of course, there's a lot of nucleophiles. You have already encountered a lot in the previous chapters. Carbonyl groups and alcohols can be interconverted by oxidation and reduction reactions. So here we have seen the reaction of an alcohol. A primary alcohol actually can be oxidized to form an aldehyde, or this aldehyde can actually be reduced not to a primary alcohol. So alcohols, you can have an interconversion between a primary to aldehyde in a reaction using the redox, oxidation reduction reaction. And you can see here, the aldehyde is a more oxidized form of the primary alcohol. The primary, you can see here that there is a loss of hydrogen, and that will be your indicator that this one undergoes oxidation process. No, it loses electrons actually in the process. You have the oxidation process. So in the reduction process, it is a reaction in which there is an increasing hydrogen content or decreasing oxygen content. So your indicator when reduction occurs for organic compounds is when you have an increased number of hydrogen or hydrogen content, or when there is a decrease in oxygen content. No, so let's say in the previous one there is a reduction or loss of hydrogen. Now you have here that is an oxidation process, and you revert back. No, you add more hydrogen, then that is an oxidation process. So example here, you have we remove the oxygen here. For instance, here from carboxylic acid to an aldehyde reaction, you'll notice that there is a reduction of the number of oxygen. Then we call this process actually as a reduction process. Okay, and here you also have your aldehyde reduced to an alcohol. You have your RC double bond O hydrogen, and you get a product of RCH2OH. This is also a reduction process wherein you actually remove, or the hydrogen content actually increases. Now from isa lang diriya, you get CH2 duha na diriya, okay, in hydrogen. So when you have an increasing in hydrogen content, that is a reduction. So the reverse of that, you have the increasing hydrogen content you have here. So baliktad siya. You can see here from an aldehyde to an alcohol, it's always a reduction process. And you can see that here in the process now the double bond actually is lost, and you actually get an alcohol. So dili siya reduction of, so if meaning a definition, reduction should be decrease in hydrogen, dili siya increase. Yeah, increase of hydrogen content. Anyway, your indicator is that whenever you have a acetyl bond O and it's converted to an alcohol, it's always a reduction process. But the reverse of forming more double bond, no, to your oxygen, no, because if you remember on how you count this one, you actually count this carbon O2 carbons here. So this one is more oxidized form. That will be your indicator. So again here for the oxidation process, increasing the oxygen content or decreasing the hydrogen content. So for example, here you have your bonded to carbon here is CH3, and you oxidize this one to an alcohol. You see how you CH3, you have your CH2. No, it's which is bonded to carbon. So this one is already your indicator that this is an oxidation process. You have a decrease in the number of hydrogen. Okay, and you see here that what is bonded to carbon is already an OH, so there is a shift, and this one is a more oxidized form than your alkane. And you oxidize this more further, you actually get your acetyl bond O, your aldehyde. Okay, so from H2, you get just RCH na wala ang isa ka hydrogen. Okay, and this is a more oxidized form. The loss of hydrogen is an oxidation, yes, is an oxidation process. And further loss of your hydrogen here, nawala, no, instead it's being replaced with an OH. It's also an oxidation process. And from here, from an aldehyde to a carboxylic acid, actually, you will see that you have an increase in oxygen atoms in the structure, and you see that this is also an oxidation process. So in general, no, from an alkane to an alcohol to an aldehyde and to a carboxylic acid, you have that oxidation process, and the highest oxidation state for your carbon here can be seen when it is in the carboxylic acid state. So a variety of carbonyl compounds can be reduced to alcohol. So for instance, you can have your carboxylic acid can be reduced to a 1 degree alcohol, or you can have your ester, RC, double bond O or R, can also be reduced to an alcohol, or 1 degree alcohol. Actually, in this process, you will get a side product, which is an alcohol, another form of an alcohol. So that will be your indicator. Normally, when you have your terminal carbonyl compounds, you actually obtain a 1 degree or a primary alcohol. An aldehyde also can be reduced to an alcohol, 1 degree alcohol. However, a ketone, you can see here that's natong si carbon with 2 alkyl groups here. You don't get primary alcohol, 1 degree alcohol, because this is not a terminal carbonyl group. What we get is a 2 degree alcohol. No? So wala tayong makitaan na tertiary, tayo form na tertiary alcohol na, because you don't have a kind of reaction. So there, aldehyde to 1 degree alcohol, but for ketone, it will be reduced to alcohol, but it wouldn't be 1 degree, but it will be a 2 degree alcohol. So carboxylic acids can be reduced to primary alcohol. We have already shown that. However, these are difficult reductions and require the use of powerful reducing agents. So imagine here in this reaction, no, from an 1 degree alcohol to an aldehyde to a carboxylic acid. So from an alcohol to a carboxylic acid, maagi pa siya aldehyde. There are actually several steps, no? And the reverse of this, when we try to reduce a carboxylic acid to an aldehyde to an alcohol, it's also a series of reactions. So if we want to reduce our carboxylic acid to an alcohol, no, we really actually need a very, very good or a strong reducing agent to do that, because before it will reach an alcohol, it will actually undergo being an aldehyde. Okay, so for the reduction of carboxylic acids to alcohols, we require the use of powerful reducing agents. So what are the common reducing agents? So whenever you encounter lithium aluminum hydride, or LAH, you have the formula LiAlH4. It's a lithium aluminum hydride. We can actually obtain our alcohol, but the process actually, no, it's a very long one. So first you can have actually get 3 moles of your lithium aluminum hydride with 4 moles of your carboxylic acid in the presence of your ether. It's a diethyl ether. No, 8Et2, it's a ethyl alkyl group, then duha, it's a diethyl ether. Okay, so we actually get a lithium aluminum tetra alkoxy here, depending na kung sa imuhang alcohol diriya or sa H2OH. So you have this product, and in the process, since you get this one being reduced, no, you actually produce a hydrogen gas, and this one is a salt, and we further reduce this one for RSH2OH. This is actually a organometallic, no? It's bonded to aluminum here. And what happened is we need to eliminate this aluminum here because this one is like a complex now with aluminum. This is lithium. This one is actually negatively charged. The whole of this RSH2O parenthesis 4. There is 4 of this alkoxy group bonded to your aluminum. And then because aluminum is bonded to 4 alkyl groups, now it will actually have a charge of negative. So that will be negatively charged, and lithium, which is passively charged. So this one is ionic. Okay, and we further hydrolyze, okay, this one with water and acid, you actually get your RSH2OH. So what you will see in the reagent is that the first step is always lithium aluminum hydride. Okay, and Et2O is diethyl ether. Okay, the first step, you get this one. The second step will be the recovery of your alcohol. Okay, so here you can just see here is pseudo bond OOH. This is the part where this can be reduced to get your H2OH. Okay, so 2 steps. So here you have 2,2-dimethylpropanoic acid. So you'll be interested only on this functional group here, your carboxylic acid. It will be reduced. So it isn't finished. You couldn't get actually your alcohol unless you get your, you need to hydrolyze that one with an acid water. Okay, get this alcohol. Otherwise, you'll just get tamadrita. It's a lithium aluminum complex with your alkoxy group. So you have to take note on the final product. So esters are also reduced to primary alcohols by using lithium aluminum hydride or high pressure. So remember, we were initially here in the previous slide, we're using carboxylic acid using lithium aluminum hydride and diethyl ether. It's also possible actually with esters. So other than carboxylic acid, pwede po siya with esters, but we use lithium aluminum hydride or high pressure hydrogenation can accomplish that transformation. So let's say you have your esters here, you have your lithium aluminum hydride, and of course your H2O, H2SO4, you actually get your RCH2OH. And then this one, since this will also be hydrolyzed, you actually get your alcohol. So there are 2 kinds of alcohols when you start with your esters. And this one, you actually should have your water here plus water. There should be another water here. In this case, since you have your OR, instead of water, you have your alcohol R prime. So whatever alkyl group here is another alcohol, excuse me, side product that you will get. Another one, excuse me, is the use of copper oxide, no, in the presence of chromium. So wala ipakita din and a very high pressure hydrogenation process like this one. So lithium aluminum hydride like this one with this reagent. So duha kinds of reagents actually with the solvent, and this one is a solvent, no, ether solvent, organic solvent. This one is in aqueous now. When you get your alcohol, it should be in aqueous. The second one is using hydrogenation very high pressure. So imagine this one, 5,000 psi. It's a very, very high pressure. You normally have like 1 atm, 25 psi. And you have here, you do this reaction at a very, very high pressure, at a very high temperature, like 175 degrees Celsius. And you have your agent, copper oxide, copper, I forget the name, CuCr2O4. It's a chromate, rather, chromate. Okay, and you have your hydrogen gas. Okay, so it's a hydrogenation reaction. You actually add hydrogen to here, hydrogen, and hydrogen here. You get your RCH2OH, and hydrogen also here. You have your ROH. No? So two kinds of reactions for esters to get your alcohol. Another one, for aldehydes and ketones, you can actually reduce relatively easily to a 1 degree and a 2 degree respectively. No? So for aldehydes, you can get, for the reduction we have seen earlier, you can actually reduce that one to an alcohol, 1 degree alcohol. For ketones, kay sandwichman siya with 2 alcohol groups, you don't expect a 1 degree alcohol, but you expect a 2 degree alcohol when you do the reduction. So what is our reagent? No, since we are using an aldehyde and ketone, no, it's not the most oxidized form. We will use a milder reducing agent. Milder, the lithium aluminum hydride is a more stronger reducing agent than sodium borohydride. So pareha rin siya, no? It will actually donate hydride. You increase your hydrogen, no? Actually, the lithium aluminum hydride is the same. This one actually will give hydrogen, no, to get your RCH2 here. Actually give your hydrogen. This is our source actually of your hydrides and nucleophilic attack, no, to your carbonyl carbon, and that is the reason why you have your hydrogen attached to your carbon here. Okay, because this lithium aluminum hydride is your source of your hydride. So ng hydride, it's a hydrogen with 2 electrons and negatively charged. It's a very, very strong nucleophile. It will attack the carbonyl carbon to get this one here. So it will attack the carbonyl carbon. So duha, kaduha. Okay. And you will get this one, H2. 2 on the other one is get your let's see later if there is a mechanism for that. You will see on the mechanism again, but just know that whenever you have a borohydride or aluminum hydride, no, it's always your source of sodium borohydride or lithium aluminum hydride rather. It's always your source of hydride, and hydride is a nucleophile with 2 electrons and negatively charged. And being a nucleophile, it will always seek a positive center. So whenever you look at the structure like here, an aldehyde, carboxylic acid, carbonyl groups, no, you always know that it will attack the carbonyl carbon, being a partially positive carbon atom. So here it's a reducing agent, sodium borohydride and water. No, what you actually get here is this one, RCH2, H2, so the hydride will attack here, and another one, the hydride will attack here, carbonyl carbon, and once the hydride will attack here, the electrons actually will go here. We'll see later the mechanism. And so here, for example, this is the general reaction here. It's a 4 moles actually of your aldehyde, and you get also 4 moles of your alcohol. Course, because you have four source of hydride, no, from sodium borohydride here, and of course you need water. But generally, no, in this reaction, instead of using diethyl ether, you can actually use a water as your solvent. So sodium borohydride here again, your hydride will attack your carbonyl carbon, okay, with electrons in it. So your source of electrons to form a bond with carbon, hydrogen, okay, na naman kay CH2 CH daan with carbon, hydrogen will be your this one, okay. It will utilize the electrons from your hydride to form here. And once it forms a bond here, the bond gikan diri paingon kang oxygen. So you will have your O minus, and of course you have your water. It will can further have you have your CH2OH in the process. Okay, and so here from an aldehyde you get a 1 degree alcohol. This is a you have butanol, you actually get your 1 butanol. This is a ketone. Okay, so once you do the reduction process with your borohydride H2O, you actually get your alcohol here, 2 butanol. So the hydrate again will attack this carbon here, and you get your CH dione. No, it will utilize the electrons from the hydride H dot dot with an electron. You will use that to form a bond here. Once the carbon and hydrogen form a bond, the electrons gikan kang carbon and oxygen, the pi electrons moadto kang oxygen. No, the oxygen now will be negatively charged, and this becomes now will obstruct the hydrogen from water to get your OH. When you can have your 2 butanol here. So again, from an aldehyde, you get a 2 degree alcohol. From a ketone, you get a 2 degree alcohol. From an aldehyde, you get a 1 degree alcohol. So let's look at on the mechanism or the key step of the reduction reaction, no? Using hydride to the carbonyl carbon. So here you have your borohydride. So regardless na kung si mong partner, you can have your lithium, your sodium. Let's say you have your borohydride here. Your hydrogen bonded to boron here. And the other one is you have your hydrogen bonded to your aluminum. No? So remember the boron and aluminum is in a group 3 and can only accept dapat to be neutral should have 3 bonds, no? But it utilizes or it uses 4 bonds with the hydrogen here, so expect the boron to be negatively charged. So the overall, no, if you remember on writing on the level structure of this, boron is bonded to 4 hydrogens rather. So the overall compound or compound rather will be negatively charged, and the charge will be on boron. Okay, so that will be your source actually of your hydride. Between boron and hydrogen, you want to disperse on the negative charge of your boron. Okay, so the electron density will be directed towards your hydrogen here, and this electron pair actually will be more directed kang hydrogen, na dili kang boron. We want to disperse this one. That will be our source of hydride. So you use the electrons gikan kang hydrogen. We attack this carbonyl carbon, which is positively charged. And once again, I have already mentioned earlier, once we attack this one, the electrons, pi electrons, gikan kang carbonyl oxygen, carbonyl group, maadto kang oxygen. So from 0 charge, mahimo siyang negatively charged, and you get your new carbon hydrogen. And where would the bond be? Where would the carbon hydrogen bond comes from? As sa atong gigamit ni electron, the electron will come from the hydride. Nganong kaniman ang gamiton? Of course, si hydrogen here will bear the more electrons gikan kang boron, because boron here is negatively charged. Okay, the direction of the electron density will be directed towards kang hydrogen, dili kang boron. Nga naman, kung ang electron density pa yung kang boron, mas ma-destabilize ang molecule. So this one, the electron density will be directed towards kang hydrogen. In fact, most of the electron density is na kang hydrogen. And we will utilize the electrons. Duha man na ka pair of electrons. So we'll utilize that 1, 2. That will be our source of electrons. That will be our source of nucleophile to attack your carbon here. And utilizing that electron diri, you use your new carbon hydrogen bond. Again, pag form na og bond, that will happen is the bond here, the electrons coming from the covalent bond will be converted to an unshared electrons here. And then to disperse this negative charge, this will attack the alkoxide ion, will attack water. This becomes your base, no? You can consider that as this will become your base. It's 6A positive center also. It's like a nucleophile that looks for a positive center. So the one will be looking at water. So hydrogen, of course, partially positive here. So negative or positive, okay, they will react. you form an OH bond utilizing the electrons from oxygen. So mawala na din ng negative charge. Oxygen will have 2 bonds and 2 unshared electrons. And of course, plus OH, plus hydroxide here. Okay, so whenever you look at the reactions, you always consider which atom will be positive, which will be negative, or which will be your source of electrons. So for example, here you have your carbonyl carbon, you think, this is partially positive. Of course, this is prone to attack with a nucleophile here. Of course, your source of nucleophile again is your borohydride. Hydride gani is hydrogen with 2 electrons and negatively charged. Okay, and in this process, once you use this one, you actually have your byproduct. Pag form ano niya, your byproduct is BH3. Okay, so it's a neutral molecule now once you get your BH3. Next. So carboxylic acids and esters are considered less reactive to reduction than aldehydes and ketones. Again, we have already answered that one earlier, no? Less reactive siya to reduction because we require the use of a stronger reducing agent. This is the most oxidized form. The carboxylic acid and the esters are the most oxidized form. You have to look at this structure. You see a lot of duha ka oxygen, no, in the structure. They are actually in the most oxidized form. The most oxidized form actually is the carboxylic acid, no, other than and after that you have the ester. So the acer reduction, of course, the acer reduction is you have